So starting with the first thing, group 2, you've got your electronic configurations. All of them have 2 valence electrons in the outer shell. So any group 2 element, for example, Mg, it's going to have 2 electrons in its valence shell. And when it loses electrons, it's always going to form a 2 plus ion. So that is an example of Mg, 2 valence electrons. All of them have 2 valence electrons, and they form +2 ions. So whenever they lose electrons, they form +2 ions, which is going to look like this. So the charge on this thing would be +2. So this is how they're always going to react. They're always going to try and form these +2 ions, all of them. And the reactivity or the reducing power, this is actually reducing power decreases. Reducing power actually increases. Down the group. What that means is, when you move down the group, you got bigger atoms. So down the groups, you've got bigger atoms, which is why it becomes easier to lose electrons. So atomic radius increases. Atomic radius increases and shielding increases when you go down the group. So that means it's easier to lose electrons. So it's easier for them to lose electrons. So the reactivity down the group is going to increase. That's one thing. And because you've got larger ionic radius. And then you have another thing, which is that the melting point decreased due to larger ionic radius. So what about melting points? They're metallic. So what happens to the melting points when they go down the group? So the ones at the top, so this is one. So let's say this is the metallic. So metallic bonding.
So what are you making?
I'm showing the metallic bonds over here. Just a second.
Okay, thank you.
Let me label this. So that's kind of enough. Anyways. So your metallic bonding looks like this. It's a bunch of positive ions, all of them positive ions, and they're all losing electrons. and they form these metallic lattices. And the electrons that are lost are kind of all delocalized. They're all present somewhere in the middle. So you've got all these delocalized electrons. This is known as a giant metallic lattice. So what is a giant metallic lattice? It's a lattice. It's a regular arrangement of positive metal ions. Of positive metal ions in a sea of free moving or mobile or delocalized electrons. So that's what giant metallic lattices are. So what happens down the group? When you move down the group, the size of the ion increases. The size of the ion increases, and charge density decreases. So this is what happens down the group, that if you have so if you have this giant metallic lattice, and down the group, the size of the lattice is going to be much bigger. The ions are going to be much bigger. It's going to be the exact same lattice, except that the ions are much bigger. If they're much bigger, they would be further away from each other, which is why there's going to be less attraction. The delocalized electrons are not going to be attracted that strongly to the ions because of the greater distance. So which is why the lattice down the group, this charge density decreases. So you've got a weaker lattice. So bigger ions means or translates to a weaker lattice. So that's all about metallic bonding. Group 2 metals are all, they all have metallic bonds. And so if they have metallic bonds, the melting points decrease down the group. Why? Because the metallic bonds, they become weaker and weaker. So that's all about this. So then you have group 2 metals and the reactions with water. Remember, the reactivity increases down the group. I told you just that. Why does the reactivity increase? Because when you move down the group, the atomic radius, so it's easier to lose electrons. So that's another very important reason. It's easier to lose electrons, which is why they're more reactive. So they're kind of more reactive. So you should know the reasons for this as well. Hanya, is this clear? Alicia, is this clear?
Yes, sir.
And then, so the first reaction, the reaction is with water. Now with water, the reactivity obviously decreases down the group. So the first one has reactivity increases down the group. So the first one has a very slow reaction with water. With cold water, it's a very slow reaction or almost no reaction. So almost no reaction with cold water. But with steam, it's going to react. It's going to be a relatively faster reaction. And the reactions become more and more vigorous when you go down the group. Calcium has a slow reaction with cold water, but it becomes more vigorous. And the solubility of the hydroxides also increases. Magnesium hydroxide is not very soluble, but calcium hydroxide is more soluble. Strontium hydroxide, barium hydroxide are even more soluble. So they become more and more alkaline as well. Uh, so that's about this. And this is about the oxide. The last three are more soluble, so you've got a greater pH. MgOH2 is not very soluble, so the pH is less than 10, around 8 to 10. The pH of magnesium hydroxide is very, very low. So group 2, not a lot in group 2 over here. I'm just going to add this. Solubility increases. So remember the pH of the hydroxides. Then about thermal decompositions. Thermal decomposition of nitrates and carbonates, and I'm going to add hydroxides as well. These three things are the ones that decompose. For example, if you have magnesium carbonate, the equations are given. Magnesium carbonate would decompose to form magnesium oxide plus carbon dioxide. You've got magnesium nitrate. Nitrates of group 2 decompose. And they produce magnesium oxide. Plus NO2 plus O2. Then you've got, and remember NO2 is a brown gas. I'm also going to talk about this decomposition of hydroxides. You heat them, they turn into oxides. And they lose a water molecule. So there are three decomposition equations which need to be remembered. And also remember that stability increases down the group. It becomes more and more difficult to decompose the compounds when you move down the group, especially with a Bunsen burner. Remember, the last two, they don't decompose with a Bunsen burner. So these two, they don't decompose with a Bunsen burner, but the top two will decompose in a Bunsen flame. Bunsen flame is around 1000 degrees centigrade. So if you're trying to decompose substances, the top carbonates would decompose, the bottom ones are not going to decompose. And the decomposition temperature of nitrates is not given, so I can just copy paste that. Group 2. So maybe it's given somewhere, just a second. Actually, so this over here is for nitrates. We can copy this. So you got carbonates and you got nitrates. Nitrates, all of them will decompose in a Bunsen burner because their decomposition is relatively easier. Carbonates, not all of them would decompose. The bottom two are not going to decompose and becomes more difficult to decompose down the group. And there's a reason for that. The reason for that is that when you're trying to decompose a carbonate or a nitrate, I'm going to take an example of magnesium carbonate. I've got magnesium carbonate is this thing. It's 2 ions, Mg2 plus, and I've got carbonate ion, which has a charge of -2. So this is what a carbonate ion looks like. And there's going to be some force of attraction that would exist between the two. And similarly, there would be, so this is MgCO3. And similarly, you're going to have, you move down the group, the only difference that will exist is, so let's say I've got barium carbonate. Now, the only difference between Mg and barium is that Mg is going to be a much bigger ion. It will still have a charge of 2+, but it's going to be a ion that would be bigger in size. Now, what that would do is that when you have barium carbonate down the group, the ions, they become bigger and the charge density decreases. So if the size of the ion becomes bigger, the charge becomes less effective. There's lesser attraction. So over here between the negative and positive ions, there's less attraction. Remember, the charge is a lot stronger if the ion is smaller in size. The charge is more concentrated, so it's going to be a stronger attraction. Hania, Alicia, is this clear?
Yes.
Okay, so always remember that a smaller ion is going to have a much stronger attraction for the negative ion. A bigger ion is, the charge is more distributed, so the positive charge is not that effective in attracting the negative charge over here. So since the first one is going to have such a strong attraction, that what it would do is that it will polarize the carbonate ion. The oxygen and its electrons and the negative charge would be so strongly attracted to magnesium that the carbonate ion would just simply break down, and the carbon dioxide would be released, and Mg would end up bonding with the oxygen in the carbonate, because Mg would be pulling the oxygen so strongly that the oxygen would break away from the carbonate and bond with Mg instead. Is this clear?
Yes.
So, and the explanation for that is written over here. That when you go down the group, the ionic radius, one second. I'm explaining this again. Remember, you've got two carbonates, magnesium carbonate, barium carbonate, and lots of other carbonates as well. I mean, you're going down the group. Now, the only difference between these carbonates is that the charge is +2, this one is also +2, this is carbonate -2, this is also carbonate -2. Everything is kind of the same, except for one thing. When you move down the group, what happens is that the size of the ion becomes bigger. So always remember that if you have the same charge, but over a much bigger area, the charge is less effective, because it's not concentrated anymore. If the charge is concentrated over a very small atom, then it's a relatively a stronger charge. How did you get this point? I mean, let's say I have this small area and there's +3 charge over here. On the other hand, I've got this really big area, and what I've done is I've distributed the charge +3 over the entire building. So this +3 charge is going to be way more effective. I mean, this +3 charge, because it's all over the place, it's not going to be attracting anything that strongly. So anyways, that was the first part. That down the group, the charge becomes less effective. Barium +2 is not going to be strongly attracting. There's going to be less attraction for the carbonate ion. Magnesium, on the other hand, would be so strongly attracting the carbonate ion that it will decompose. It will be so strongly attracting the oxygen over here. I mean, this oxygen over here, it will be so strongly attracting this oxygen that the oxygen will simply break away from the carbonate and join the Mg to form MgO. And the carbon dioxide would break off. Hani, do you get the point?
Yes, sir.
So this one decomposes the first one decomposes easily. Like you don't have to provide it with a lot of energy because the Mg would do everything to decompose it. Barium would not help in the decomposition process. I mean, the carbonate ion would be a lot more stable. So the explanation for this is why do they become more stable down the group? Why are they harder to decompose? The reason is that when you go down the group, ionic radius increases and the charge 2 plus its charge density decreases. Hence, the ion polarizing power decreases and the carbonate or nitrate ion, they become less polarized down the group. Or you can say that they become more stable. TK, is this clear?
Yes.
Now, the very last thing is about the uses. Remember, MgO is used in refractory lining. Mg, it's a compound of Mg, and it's an ionic compound. It's a very, very strong compound. It's used as a ceramic. So this one over here is a ceramic material. So ceramics are anything. They're anything that has that are really strong, tough. They've got very high melting points, boiling points. And they also have, they're very good insulators as well. So why is it so strong? Because it's got a very strong lattice. Mg ions attracted to oxygen -2, which are then attracted to Mg+2, which are then attracted to, and so on. It's just an endless lattice of Mg+2 and O -2 ions all attracting each other. So it's a very strong lattice. It's got a very high melting point. So it's used as refractory lining, which is basically you make furnaces out of it. Calcium carbonate is a very popular thing because it's limestone, which is everywhere. So limestone, it's used in making steel and glass, and it's used to make lime, which is often used to make cement, mortar, and limestone is used. Lime and limestone are used to neutralize acidic soils. So lots of things happening over there. You should remember the flame test as well. What are the colors of the flames for Mg? Calcium, strontium, and barium. Barium is apple green. Strontium is scarlet red. Brick red is for calcium. And Mg has a white flame. So you have to remember all of this in group 2. So we're going to do a couple of questions now. Group 2 is really small. It's not, there's not a lot to it. Just the melting points, reactivities, etc. Those things, reactions with water, that's one. The decomposition of carbonates, the solubilities of the hydroxides. And we can also add the solubility of the sulfates as well. Or we can generally talk about the solubilities of all the other compounds, since we are talking about solubility, so group 2 compounds. So just for group 2, I'm going to write down the solubility of everything. So group 2 carbonates and phosphates are all insoluble. Then group 2 sulfates So group 2 sulfates become more soluble down the group. So I'm going to talk about this sulfates, the solubility of the sulfates. So the first one become less soluble actually down the group. So the bottom two are insoluble. This is partially soluble. And MgSO4 is the one that's soluble. So remember the solubilities of these compounds. Chlorides are all soluble. And also nitrates are all soluble. So that's about it. That's group 2. So we're done with PhD and we're done with we did PhD, completed PhD earlier, and we're done with group 2. What's left is halogens now. Okay, so this is all the stuff that you have to memorize and remember. So we're going to try and do a few questions, but what we can do is we can just go through or start with halogens as well. So we can try the
Sir,
yes.
could you please make the playlist of organic chemistry and inorganic chemistry's videos, because I want to review them on the weekend.
Okay, for this one, sure, I can send you the 2 lectures for this one. And for organic, the problem is I've got a lot of lectures, but I mean, this is how it looks like actually.
I just need the last ones. Remember when the ones that were taking the October test, when they had their CIEs? Just the ones after that.
Just 1 second. I'll share you the document link which has all the lectures. Just a second. It's this one, right? Yep. So these are all the lectures. I'll share this. This one is the one I think, or probably not this one. I'm not really sure. I'll just check. So I'll share this. It's got all the videos for 9th September and I think at the end of August. So it should contain all the lectures. So I'll share this folder.
Thank you. And if you could please send me yesterday's inorganic chemistry class too.
Okay, I'll share this folder. So what you can do is I mean, you can check the time. I mean, it's a AS new session, so it's probably this one, I think. So I'll share that with you, okay? I'll share the folder. The only thing is it's kind of a bit unorganized at the moment, okay? But I'll share the folder with you. I mean, state-wise organized, so you can sort of go through and you can find the next lecture. Mainly it's AS new session.
Thank you.
So let's start a bit about halogens. About halogens, you've got the first thing is the trend in volatility and the color. That's the first thing. So halogens, starting with fluorine, chlorine, bromine, and iodine, they're all diatomic. The first one has a very pale yellow color, or you can say that it has no color at all. The next one is greenish yellow. Bromine is an orange brown or reddish brown liquid, which is kind of volatile as well. And iodine is blue black solid or purple vapor. Iodine has several colors actually. So I mean, just by looking at it, if you look at iodine, it's a blue black crystal, which you can see over here. But if you talk about iodine vapor, then the vapor has this color, it's purple in color. And then if you look at iodine aqueous solution, then that aqueous solution is brown in color, which is kind of probably not this one. Is this iodine? This is iodine. So it is brown in color. So it's got three colors actually. So remember this about iodine blue black solid or purple vapor. I'm going to add the one that's missing, and that is what is missing, that it is brown in aqueous state. So yellow or brown. Same goes for bromine as well. Because bromine also it becomes reddish brown when it's a vapor. So anyways, the colors are changing, and the states are also changing. This one is a liquid. The melting and boiling points, they increase. Why do they increase? Because the temporary dipole induced dipoles, they become larger due to size. Remember, what was temporary dipole induced dipole? The only attractive force, because it's a non-polar molecule. For example, if you look at a Cl2 molecule and you look at another Cl2 molecule, they're both non-polar. The only thing that happens is that during collisions, the dipoles would fluctuate. I mean, sometimes this side electrons would bump or shift to the right. So this side would become slight negative, this side would become slight positive. And because of the negative charge over here, the electrons in this molecule would also get pushed to the right. This side would become slight negative, this side would become slight positive. And then due to some random reason, the molecule might bump and the electrons might get shifted to the left. So this side would become slight negative and this side would become slight positive. The positive side will attract the electrons from the other molecules. So the other molecules' electrons will get attracted to the left, and which is why this side would become negative and this side would become positive. Anyways, but so this is instantaneous dipole, induced dipole. So temporary dipole, which then induces a dipole. So that is van der Waals forces. The two dipoles will attract each other. The positive side of this molecule will attract the negative side of this other chlorine molecule. So they're going to have a lot of van der Waals forces. And that's the only force that these molecules, these things will have. So van der Waals forces depend on size. If you've got more electrons, there would be more van der Waals forces. If you've got more electrons, there would be more temporary dipole induced dipoles getting formed. So iodine has a total of 53 electrons. So that's a lot of electrons. So there would be a lot more dipoles in iodine compared to chlorine compared to fluorine. So van der Waals forces become greater when you go down the group. Is that clear?
Yes.
So down the group, you've got more electrons. And there's going to be more van der Waals forces. And more TD ID forces, temporary dipole induced dipole forces. So we'll probably finish this in the next class, group 17, and that would pretty much be the end of all the 4 topics for inorganic. Okay. Achanya, I'm going to share the folder with you. Okay. I'm sending it in the WhatsApp group. Okay.
Thank you.
Okay, then take care. Allah
Allah
Hafiz.
Hafiz, sir.
Allah Hafiz.
Thank you, Allah.